Hi, calculus. We are moving on to 3.2 and 3.3. So we start with this idea of continuity, a continuous function. Okay, for example, here's a function. It is Congress passed legislation raising the federal minimum wage for the third time in 3 years. Figure 13 shows how that wage has varied since it was instituted. We denote the function by f of t, where t is the year. Okay, so between 1940 and 1950, it was here. I guess 1938, it looked like, or no, 1938 is where it started. Okay. But anyway, this was the minimum wage, and it was the same for a while, then it jumps up. It's not like it's, every dollar in between. Okay, this is a step function. It is a function. If I drop a vertical line, it doesn't hit twice anywhere. Okay, it wasn't like you didn't have two different minimum wages in 1940 or something. You had the same minimum wage. It's just it jumps. Okay, this type of function is not going to be a continuous function. Intuitively speaking, okay, sorry, let me ungroup this a second. Intuitively speaking, a function is continuous at a point if you can draw the graph of the function at the vicinity of that point without lifting your pencil from the paper. Okay? It's continuous if you can continually draw it, if it doesn't have any of these breaks. Okay, if I was going to trace this, I would just be able to trace it and never have to lift up my pencil. That's intuitively. Here's the mathematical definition. A function is continuous at a point x equals c if these three conditions are satisfied. The function has to be defined at that point, okay? You have to be, if c is a number, right? Okay, so if I put c into my function, I get a number. So if I put 2 in, there's an f of 2 that exists. The limit as x approaches c of that function has to exist. Remember what that means. That means it has to be the same from the right as it is from the left. That's what the limit means. And the answer to number 2 here has to equal the answer to number 1. Okay, they have to equal each other. Those are the conditions that have to be met for a function to be continuous at x equals c. Okay, so let's look at these. Are the functions continuous at a given point? Here's f of x. Is it continuous at 3? Well, if I was going to trace it, I'd have to lift my pencil up to continue. Okay, but the reason it's not continuous, you're right, it's not continuous, is because of number 1. So let's go back and see. Number 1 was f of c has to be defined. I don't have an f of 3.
At this time, all students in odd number.
Sorry about that. Anyway, the limit exists. Okay, it looks like the limit as I approach 3 is 2, right? As I approach 3 from the left and from the right, I get real close to 2, but I never actually hit it. Okay, or maybe 2.1, I don't know, but the limit does exist. Number 2 is fine. It's just number 1. I don't have an f of 3. Someone says, what's the y-coordinate that goes to 3? I don't know. There's an open hole there. The function doesn't exist. Okay, and of course, if either 1 or 2 doesn't work, that means 3 doesn't work. But we would say that right away this failed at number 1. Here it says, does this function exist at 0? Not exist, I'm sorry. Are the functions continuous? Is h of x continuous at 0? Well, I know number 1 works. H of 0 is -1. Okay, when I put 0 in, the point 0, -1 is a point on this graph. Okay, however, the limit as I approach 0 from the left is -1. The limit as I approach 0 from the right is 1. Okay, therefore the limit as x approaches 0 of h of x does not exist. Okay, I have a functional value, but the limit doesn't exist. So the reason for this was no, by number 2. Okay, the limit didn't exist. Here's g of x. If you can see this graph here, okay, it's a line except for at 4, the 0.41 is on the graph. So number 1 works. Is f of 4 defined? Yes, or in this case, g, I'm sorry. Is g of 4 defined? Yes, g of 4 is 1. The y-coordinate that goes with 4 is 1. Number 2, does the limit exist? Sure. As I approach 4 from the left, it looks like I approach 2. As I approach 4 from the right, I get close to negative 2. I'm sorry. The limit as x approaches 4 is negative 2. So f of 4 is 1. The limit as x approaches 4 is negative 2. So this fails because of number 3. 1 works, 2 works, but they don't equal each other. Okay, so this one is no by number 3. Okay, and then this last one, are the functions continuous at a given point? At x equals negative 2, this asymptote. Okay, basically there is no f of negative 2. There's no point negative 2, 10, negative 2, 100. I don't know what, there is no negative 2, blah, blah, blah. Okay, so this one is also fails by number 1. Okay, sometimes that means there's a hole. Sometimes that means there's an asymptote. Okay, if number 1 fails. Okay, so I just wanted you to see the different ways that these continuity things don't work. Okay, this one was number 1. The limit existed, but there's no f of 3. This one, hey, you have f of 0. We were checking for around 0. We have f of 0, but the limit doesn't exist. This one, we have f of 4, and the limit exists. They don't equal each other. And this is another one example where f of negative 2 doesn't exist. Okay? Now, if you could just add or move 1 point, and then the function would be continuous, we call that removable discontinuity. Figures 14 and 16 were examples of removable discontinuity. Okay? Number 14, all I'd have to do, if I could, there, I'll put 1 point right here at 3, 2, continuous. Here, I move this point to here, done, continuous. This one, I mean, even if I'd fill this in, it's still not continuous. If I move at 1 point, not a bunch of points, 1 point, nope. This is not removable discontinuity because I can't get rid of the discontinuity by just doing one thing. Here, I can't remove this discontinuity by just putting a negative 2 point because this is still just getting close to negative 2, whatever. Okay, so removable discontinuity is when you can just add or move 1 point and then the function would be continuous. Okay, then we talk about continuity on a closed interval. A function is continuous on the closed interval from a to b if it's continuous on the open interval from a to b, and it is continuous from the right at a and from the left at b. Okay, so this is like from negative 1 to 1, where negative 1 would be a, 1 would be b. Okay, it is continuous everywhere, okay, from negative 1 to 1, not including them. That's what the parentheses mean, not including negative 1 or 1. It's continuous as I approach from the right. It's continuous to negative 1. As I approach from the left, it's continuous at 1. Okay, it's just, it's hard to call this continuous at negative 1 because from the left, it doesn't even exist. Okay, and we can't say from the right to B because to the right of 1, it doesn't even exist. So that's why when it's a closed interval, we're looking at the open interval for continuity, and then we look is it continuous from the right to the left endpoint and from the left to the rightmost endpoint? Okay, this is the function. The function that's graphed there is actually the square root of 1 minus x squared. It's continuous on the closed interval. By defining the continuity on the closed interval in this way, we need not worry about the fact that the square root of 1 minus x squared doesn't actually exist to the left of -1 or to the right of 1. Okay, we define continuity this way when we're talking about a closed interval. Okay, so here are some continuous functions. Polynomials, oh, I love them. They're continuous everywhere. Everywhere. You never have to worry about a polynomial. Rational functions, let's think about it. We do have to worry about something, don't we? We have to worry where there's asymptotes, vertical asymptotes. Okay, so a rational function is continuous everywhere except where the denominator is 0. Okay? So it's continuous everywhere except where the denominator is 0. Root functions, square root, they're continuous for all x as long as what's under the square root is greater than or equal to 0. Okay, we can't have negatives under the square root. Exponential function is continuous everywhere as long as, of course, this a is bigger than 0. That's the definition of an exponential function. And log functions are differentiable as long as x is bigger than 0. Okay, because remember we have a vertical asymptote for log functions. So that just gives you an idea of the different types of functions and their continuity. So let's practice this. I have a rational function here, and it's asking me for all values of x equals a, where is the function discontinuous? Find all values where f is discontinuous. Okay? All right. So I'm looking at this. It's a rational function, and I realize it's going to be discontinuous wherever the denominator is 0. So that's going to happen at 3.5. So find all values where the function is discontinuous. It's discontinuous at 7/2 or 3.5 or 3.5. Okay. Letter B is an exponential function. E is 2.718. You know, it's that weird long number, irrational number, but that's bigger than 0. So this is continuous everywhere. All real numbers. Okay. I don't know. There's different ways the book. Sometimes they say negative infinity to infinity for all x, all real numbers. Okay, this is continuous everywhere. Stick any x in you want. Positives, negatives, doesn't matter. 0. Okay? And the last one is a piecewise function. Notice the domain goes less than 1, from 1 to 3, and bigger than 3. So this is defined everywhere. We just want to see what's happening at 1. Okay, I want to make sure the limits are the same. If I put 1 in here, I get 2. If I put 1 in here, I get 1 minus 3, that's -2, plus 4, that's 2. Great. So I'm fine at 1. Okay, now let's look at 3. If I put 3 in here, I get 3 squared is 9, minus 3 times 3 is 9. So that's 0 plus 4 is 4. If I put 3 in here, 5 minus 3 is 2. So f of 3 equals 4, because notice that's where the equal sign is. Okay, f of 3 equals 4. But the limit as x approaches 3 is different. It's 2 on this side and 4 on that side. So this is not continuous at x equals 3. Okay, because it was defined kind of in these two ways. Okay, see you for the next part.